everyone, myself is Deviation, Assistant Professor in Chemical Engineering Department at LJ Institute of Engineering and Technology. The subject that we are going to continue is Mass Transfer Operations 2. Okay, so as far as last lecture was concerned, we covered the topic that was effect of pressure on VLE. Okay, now in this lecture we will study about deviation from ideality. Okay, how when your real solution you take into account. Okay, when you are talking about real solution, how it is different than ideal solution. Okay, so first of all, let's have a quick revision that for an ideal mixture, okay, how we define the definition of partial pressure. For an ideal mixture, the partial pressure is related to the concentration in liquid phase by Rolle's law. Okay, so in ideal mixture, the partial pressure is related to the concentration in liquid phase by Rolle's law. Okay, we had defined that Rolle's law. The definition was given as it is product. Okay, the partial pressure of your more volatile component in a mixture. Okay, that was discussed earlier in earlier lectures also. For a binary mixture, okay, A and B, the partial pressure would be of any one component. Okay, let's talk about A as my more volatile component, and so the partial pressure of this more volatile component is product of vapor pressure of A into mole fraction of A in your liquid phase. Okay, so that is my definition of partial pressure using Rolle's law. But I can also define my partial pressure as product of vapor phase mole fraction and total pressure of the system. Okay, hence I can get my YA as vapor pressure of A into mole fraction of A in liquid phase upon total pressure. So this is my YA. Okay, now if the mixture follows Rolle's law, then the values of YA for various values of XA may be calculated from the knowledge of vapor pressure of two components at various temperature. Okay, we will solve some questions also. These are some very simple questions. Okay, when you have to find either YA or XA, any of the data would be given. It is totally manipulation of your equations, how you are calculating PA or PB, PT. Okay, so we will follow an example later on. So simply you are given, okay, you can calculate the value of YA, okay, for various values of XA. So see, using this equation you can also generate an equilibrium data, okay, YA versus XA. Now one thing you have to take into account, into note, that vapor pressure, okay, it is function of temperature. We will see how. So the vapor pressure of any component is a function of temperature. Okay. So there are many equations which relate pressure and temperature. Okay, one of it is Antoine equation. Okay, so Antoine equation is given as log Psat is equal to A minus B upon C plus T. So A, B, C, what are these? These are some empirical values which would be provided. But see, as you are changing the temperature here, you can calculate your Psat that way, right? What is your Psat again? It is vapor pressure. So as temperature changes, okay, as I am keeping different value of temperature, corresponding to that temperature, I will get my vapor pressure. Okay. Again, have a quick revision about boiling. See, as you are changing the temperature, more and more vapors are formed. Okay. So what is vapor pressure? What is vapor pressure ultimately? It is the pressure that is exerted by vapor on liquid phase. So as you are changing the temperature, your vapor pressure is also changing, right? So hence we can say that this is the equation, Antoine equation. It relates vapor pressure with temperature. So I am telling you, so suppose an exam, you have given a question, okay, at temperature is equal to 100 degrees Celsius. Okay, so at 100 degrees Celsius you have to find your vapor pressure. So A, B, C would be given, and accordingly you will calculate your vapor pressure. See, for pure species, your partial pressure is what? That is equal to vapor pressure, right? Try to understand it. Okay, in the TXY diagram and PXY diagram, okay, when I am talking about the vapor pressure of that in the diagram, so that was about pure component. Okay, when your component is pure, okay, talking about single A only. Okay, so at that time what is A? Okay, what is the partial pressure? That is equal to vapor pressure, and that is equal to your total pressure of the system. Okay, so for ideal solution, let's have a look. Okay, this is the graph of vapor pressure versus mole fraction. So for ideal solution means Rolle's law is applicable. So your OA line, okay, your OA line, what is it? It is partial pressure of A which is changing with mole fraction, okay. And what is BC? It is partial pressure of B which is varying with the liquid phase composition, again X, okay. So my total pressure, what is it? PA plus PB, okay. PT, what is total pressure? Partial pressure of A plus partial pressure of B from Dalton's law. Hence, substituting the value of partial pressure which we defined using Rolle's law, XA into PA sat plus XB into PB sat. So you can see PA is equal to what? XA into PA sat. If my component is pure, so XA would be what? 1. Hence your partial pressure is equal to vapor pressure, and that is equal to total pressure, okay. Again try to recall it. When I am talking about a single cylinder, in a single cylinder I am keeping only one gas A. So it is pure, it means XA, mole fraction of A is 1. Hence its partial pressure would be equal to vapor pressure, and that is your ultimately total pressure. But when they are mixture, when there is mixture, okay, so hence then the definition of your partial pressure is, because now you are going to have mole fraction also. So hence PA is equal to XA into PA sat. So you can see vapor pressure versus mole fraction diagram. Your A is there and B is there, okay. So at A point, what is A point? That is vapor pressure of your pure A component. And what is B point? That is vapor pressure of your pure B. But in between, your mole fraction is varying now, okay, of your volatile component. So OA line, what does it show? It shows the trend of PA, okay. As XA would change, you can see from equation also of PT. As XA will change, hence XB will also change. What is XB? It is 1 minus XA, okay. It is given. So hence as XA will change, your PA value will also go on. So you can see it is showing the trend of partial pressure as your mole fraction changes. And ultimately, what is AB? Your AB is nothing but your BA, okay. The line BA is the total pressure of the system, of this ideal system, okay. It is the total pressure of ideal system. Yeah, that is the total pressure. So you can see again once more, your OA, what is it? It is partial pressure of A which changes with X, okay, at certain point. Let's take an example at D mole fraction, at D point. A mole fraction is defined, okay. So for that mole fraction, what is DE, line DE? It is partial pressure of A, okay, for D mole fraction. At D point, your mole fraction might be something, let's say, take an example, 0.2. So for 0.2, you can substitute the values. Your PA sat is defined, okay. Your PA sat for pure species is defined, okay. So it would be given in exam that the vapor pressure of your pure species. Again note down, vapor pressure comes into account right for pure species, okay. It is defined for a pure species. Partial pressure is what? Partial pressure is equal to vapor pressure when your component is pure, again pure. When XA is 1, then only PA is equal to PA sat. But when I am talking about mixture, your partial pressure will vary, okay, as your mole fraction changes. So your partial pressure of component A would be given and B would also be given, okay. Now for D point, your mole fraction, suppose we took an example, let mole fraction is 0.2, okay. So at 0.2 your PA would be 0.2 into PA sat. So that way calculating you will get your total pressure. So this is for ideal system, okay. This above graph, it is the relation and graph for ideal mixture, because your Rolle's law is applicable. Now what is non-ideal mixture, okay. For non-ideal mixture, it does not follow Rolle's law, okay. In non-ideal mixture or real life example, okay, real mixture, we don't take into account the ideal conditions, okay. The ideal conditions which would assumed was that intermolecular force of attraction was not existing. This other was volume was negligible, but that was the assumption for ideal conditions. Now in real case, intermolecular force between molecules do exist. Also we cannot neglect the volume. So to take into account this non-ideality, we add gamma, the activity coefficient, in the formula of Rolle's law, okay. So you get your calculation now as YA is equal to gamma 1 PA sat XA upon P. Okay. So whereas for ideal system we had YA and YB as given below. Okay. The second formula of YA and YB, that was calculated using Rawls law. Whereas for non-ideal system, you are adding a correction kind of activity coefficient is what? It is converting your ideal system formula into non-ideal system formula. Your gamma is again what? It is the activity coefficient. Okay. Now, hence for non-ideal system, the partial pressure is now your different. Okay. Because let's give it a name. It is observed partial pressure for the real mixture. Right. So what is gamma again? Gamma is the measure of non-ideality in solution. Okay, how your non-ideal system is deviating from ideality. So here assumption is that, okay, your VLE, in thermodynamics you might have studied the modified VLE equation, okay, where you are taking into account non-ideality of gas and liquid solution both. But here for distillation purpose, okay, to study the non-ideality in distillation, what we are doing, we are assuming that gas follows ideal behavior, but your liquid do not follow ideal behavior. Okay, so hence we are giving certain terms. Okay, here PA observed, it is observed partial pressure of A for non-ideal solution. Similarly, B is observed partial pressure of B for non-ideal solution. Okay, we are differentiating the terms here. Once more time, gamma is your measure of non-ideality in solution, okay, and PA observed and PB observed are the observed partial pressures of A and B for non-ideal solution. Okay, now we are getting into non-ideal mixtures. So you can see OA. Okay, what is OA line? OA line is the partial pressure of A, okay, in ideal solution. Okay, it is the straight line. Okay, the straight line, it shows the variation of partial pressure as the mole fraction changes. But curve B, okay, it is partial pressure of A for non-ideal solution. You can see the deviation. Okay, now for this non-ideal solution, of course your total pressure would be different. So here your total pressure is summation of observed partial pressure of A and B. Okay, again take into account this is for non-ideal solution now. So here your partial pressure would be gamma A XA into PA sat plus gamma B XB into PB sat, where your gamma A and gamma B, what are those? Those are the measure of non-ideality. Okay, so hence your total pressure is now different than that which we calculated using ideal solution, okay, when Rawls law was applicable. So that was for today's lecture. In next lecture we will see how different deviations are. Okay, we here saw that for non-ideal solution your partial pressure is now different. Okay, your partial pressure and even your total pressure is different. See here there are two conditions. Your gamma, that is activity coefficient, may be more than 1 or less than 1, and based on that you have different type of deviations, that are positive deviation and negative deviation, that we would cover in next lecture. But for till now we saw the difference between ideal solution and non-ideal solution. For ideal solution, Rawls law gives you the relation of partial pressure mole fraction. Okay, but for non-ideal solution a new term, activity coefficient, is introduced. So here your partial pressure and total pressure both are different than that which we calculated in ideal solutions. So here again you can see OA is the straight line. Okay. So here we finish the topic of our non-ideality. In next lecture we will continue with positive deviation non-ideality and negative deviation non-ideality. Thank you.